This is video 4.1. It deals with magnets. So magnets is something we're fairly familiar with. We know that they exert forces. They can be repulsive or attractive. They can also induce, which means to create indirectly magnetism in magnetic materials. So iron being the most obvious one. So a permanent magnet, when brought close to a magnetic material, temporarily turns it into a magnet, if you like, as opposed to being permanently. So it then displays magnetic behavior in the sense that it will be attracted. We also have the concept of fields around magnets, so areas where force is experienced. And we're going to talk about the Earth, and we're going to talk about flux lines, which is just a posh word for field lines, really. So first of all, we've got field lines, so these lines that connect north and south, and we have the idea of attraction. So north and south will attract, and the shape of the field will change depending on how close they are to each other. Now the opposite situation is when we have two likes. Our example here is two norths, and the field lines now don't meet. They're doing anything but meeting, and we get repulsion. Now here we've got the difference between permanent and induced magnets. Now these tiny magnets that we can see represented here are called domains. So in the permanent magnet they are permanently aligned, as you can see, whereas in the magnetic material over here they can be, or at the beginning they are all over the place, but they are forced into line, they are aligned by the magnetic field from the permanent magnet. And you can see they swing in the opposite direction, so now all the souths, the blues, are all facing left, and that's why they always attract. There's no such thing as an induced magnet that will be repelled by the permanent magnet. So we've got a number of ways of investigating magnetic fields. The two classic examples shown here are iron filings, which are made of iron, funnily enough, and so they will align according to the field, so we can see the field lines, a physical representation of them. And we can also use compasses, which will do a similar thing. In essence, the filings are tiny compasses. So when we have a high density here, high flux density, that means the field is strong, which relates to our common sense. When we're close to a magnet, the strength is greater, and it's less further away. We also have the sense of direction. It's fairly obvious that all these are trying to align, and so on. So finally then we have the biggest magnet around, which is the Earth, and we have the slightly weird situation where the North Pole is a South Pole, which is a bit confusing, but that's the way it is. So the North Pole of a magnet is defined as the pole that, when the magnet is freely suspended, points towards the Earth's north magnetic pole. So if we call that the Arctic for a moment, to get away from that phrase, this points towards the Arctic, and we call that the North Pole because that's what the North Poles are pointing at. But as we know, opposites attract, so it must actually be a magnetic South Pole. A bit confusing, but there we are.